this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We've gone through a lot of measurements, and we've actually alluded to a huge number of things that may or may not be occurring with stars. We've said that stars live, they have distances, they may even have run out of fuel. But we studied the Hyades star cluster in order to understand spectroscopic parallax, and we looked at the Pleiades star cluster to also help us with understanding parallax. But we really didn't discuss what the nature of star clusters are. So if you see in the background of this image, we just see lots of stars evenly distributed. But stars do not come evenly distributed. They come in clusters and groups as well. So let's look first at our friend the Hyades star cluster, which is the nearest star cluster to us at about 47 parsecs, or about 150 light years away. It's also pretty young, and its main sequence turns off indicates it's only about 600 million years old or so. So it's a young star cluster, and the cluster itself is kind of hard to see because it's so spread out because it's so near to us. So let's look at some other star clusters. And what do we mean by main sequence turnoff? We mean that there is a series of stars that are bluer than a certain value in the B minus V. And that turnoff will tell us the age of the star cluster. That is the trick for today. So I gave it all away, but let's develop that whole idea. Here is the Gaia study, which actually then shows, which we showed last time, which was that line that goes all the way across. That black line across is a computer simulation of exactly when the stars run out of fuel. And when they run out of fuel, specifically hydrogen fusion in the core, that top area, way up in the upper left, is where that kind of goes off to a squiggle, sort of straggle. So you have the main sequence, which is almost a straight line going from lower right up to upper left, and all of a sudden it becomes a squiggly squiggle. That squiggly squiggle is what happens to the star when it runs out of hydrogen in its core. The exterior of the star changes in both brightness and color as the star leaves the main sequence. Once again, the HR diagram is the central tool for all astrophysics, and this is again the Hipparchus view of nearby stars, about 22,000 stars. And we don't see a main sequence turn off here because we're looking at a lot of stars. However, we do see a group of stars called giants and a group of stars called white dwarfs. And we're going to see where those giants and white dwarfs actually come from at this point. So star clusters, what are they? We're going to use star clusters to get us there. So star clusters are grouped, maybe a few hundred stars to many thousands to hundreds of thousands, if not millions of stars moving together through space. And all the stars in the cluster are roughly at the same distance. So if you measure the brightness, you're measuring their relative luminosities, or how luminous they are with respect to each other. And because they're clusters, we're assuming they all have the same age of stars in that cluster, because we're assuming that they were all born together at once inside that cluster. Now, the other thing we're assuming is because they were all born at the same time, they roughly have the same chemical composition, meaning how much more of hydrogen and helium, all the other elements heavier than hydrogen and helium they have. And we also find that they have an enormous range of stellar masses. And it's that last point that really tells us a lot of everything about the star cluster. So the cluster provides snapshots. All right, so here's what we're going to look at. So we have two different types of star clusters that we've observed in the sky, open clusters. They're fairly sparse. They're not spherical distribution. They're a few hundred to 1,000 or so stars, a couple of parsecs of tens of light years in diameter. They have many blue main sequence stars and only a few red giants, and they tend to be relatively young at a few 100 million years. Now, globular clusters, on the other hand, are spherical. They have lots of stars, between 100,000 and about a million stars. They're about 10 to 30 parsecs in diameter, so they're a bit bigger than open clusters. And there are no blue main sequence stars, no O stars, no B stars, no A stars, no Fs, very few Gs, if any, and many, many, many giants and red giants. Their ages tend to be about 8 to 12 billion years old. So open clusters tend to be young, and open clusters are young, globular clusters are old. Let's look specifically now at open clusters The HR diagrams for open clusters show that they are young to middle-aged, meaning young to middle-aged is somewhere up to about 2 to 3 billion years, depending on how big they are. They have blue main sequence stars, very few supergiants or giants, and they have old open clusters, have a few red giants. That might be how you distinguish them. And you don't see any horizontal giant branch stars, which is a group of stars that are burning helium in their core. The youngest open clusters have gas clouds associated with them, such as maybe the Pleiades and others as well. But mostly you have to look at them in star forming regions, which we'll talk about in a future lecture. So let's look at some of them. Now, what do we mean by a star cluster? Well, this is a really good way to begin the concept of a star cluster. And I grabbed this from Wikipedia from a guy who has his own website called Raw Astrodata, but this tells us a lot. Now, you think of stars as evenly distributed across the sky. And in a two-dimensional setting, you can definitely see there's lots of stars here. And we got some dark areas. Those are called dark nebulae. But we're really focusing on the overdensity of bright stars just below center. And that overdensity is called Messier object number 11, named after Charles Messier, who made a catalog of such bright objects back in the 17th century. What we see here is a cluster. It is an overdensity of stars, or a grouping of stars that tend to be brighter or more prominent than the evenly distributed background stars. And that's what we mean by a cluster of stars. So this is a star cluster. And now we're going to take a look at a whole bunch of different star clusters in the sky. And if we do a zoom close-up of Messier 11, it has its own special name. It's called the Wild Duck. And it's about 2,000 or almost 3,000 stars living at about roughly 2,000 parsecs, or about 6,000 light years away. And you can see it in binoculars as well. And its age has been estimated about 250 million years. That's older than the dinosaurs. So if this were in the sky, the dinosaurs would have been able to see this thing in the sky as it formed. And probably back then it had a star cluster, had a gas cloud around it from where it formed, such as the Orion Nebula. And now the triangular shape is where it kind of gets from it. It's these odd names that people come up with for astronomical objects are really fun and very historical. So if you go Google around, you'll find that there's all sorts of funny names. And the reason that it's called the Wild Duck, maybe it's because it's a triangle of flying ducks or something. And the guy, instead of calling it the Wild Goose Cluster or the Wild Robin or the Wild Duck, the Wild things, he just thought lots of ducks flying in a triangle. That's interesting. In any event, another prominent open cluster is the Pleiades, or Messier object 55. It's got about 3,000 stars in it, lives about 400 light years away. About 13 light years across is the group of stars that you see in the center. And there's a bright reflection nebula, that's that blue glow, that's wispiness around it. And that's because the star cluster is passing through that nebula. And as it does so, it illuminates that nebula. All right, there's another example, is one of my favorites that you can go see in a small telescope, the Perseus Double Cluster, or NGC 869 and 884. It's two clusters that are approximately 7,000 light years away. And it's been seen for a very, very long time. And it's been noted, it was even noted by the astronomer Hipparchus, who gave us the name for the magnitude system, as well as giving us the idea about looking for brightnesses of stars. Those two clusters are separated by a couple hundred light years and are much younger, and many of the stars that are much younger and hotter than the sun. So let's zoom out and look at another star cluster, M67. That M11 was a very, very deep photograph, so it kind of masked what we would think about it. And M67 contains about 500 stars, and it lies almost 3,000 light years away in the constellation of Cancer. And with this, so if you're looking at this, that group of stars, that cluster in the center, is about 12 light years across. So that's kind of a dense little downtown sort of area. And that's what it's another kind of open cluster. Notice there's some space between them. Another name for open clusters are galactic clusters, because they're always situated in the galactic plane. So another one is Messier object number 457, and it's an open cluster in Cassiopeia. And we see a whole number of them. There's some bright stars in the center there. The overdensity of stars there. The age of this one, it's a relatively young one, about 21 million years. So it was not visible. If you went back 60 million years, you wouldn't be there in the sky. And it's almost 8,000 light years away. And there's a few thousand stars. In general, open clusters are up to about a few thousand stars, and they're formed from the same giant molecular cloud, and they have roughly about the same age. So let's look at now let's look at NGC 663. It's another open star cluster, about 400 stars. That's that overdensity in the center with the bright center stars there. Its age is about 20 to 25 million years. And stars of spectral class B2 or higher, the O's are gone, are gone, but B2 are reaching the end of their main sequence lifetime. The open star clusters are generally mutually gravitationally bound. But as they move through space, there's lots of stars out there. They eventually get kind of close to maybe some other star clusters, so they get disrupted. And even the stars inside of a star cluster themselves can swing around each other and get flung out into space. And so eventually star clusters disperse. And here's another prominent one, Messier 36. It's about 4,000 light years away, about 14 light years across, and it's got at least 60 members in it, and it's similar to the Pleiades, and if it were that distant, it would be about the same brightness in the sky. Now, such star clusters only survive as their trip around the Milky Way a few hundred million years before the stars get dispersed because of that. And open clusters are also only found in spiral-type galaxies, which is where star formation occurs. So they are centered in star-forming locations. Once again, there's number Messier 41, one of the most prominent in the sky. If you look in the big dog, Canis Major, it's about just really close to almost exactly south of the bright star Sirius. So if you want to go find an open cluster, find the brightest star in the sky, Sirius, which follows Orion in the sky, and then just take 4 fingers widths due south from it, and that's where it is in the sky. There's about 100 stars, a number of white dwarfs, and a bunch of white dwarfs and red giants in there. And we have the average Doppler shift shows that it's rushing away from us at about 23 kilometers per second. And the diameter of the cluster at that distance is, well, not at that distance, but the diameter of the cluster is about 25 or so light years, and it's about 100 million years old. And all these pictures that I've shown you in the past bit have the same proportion, the same kind of black and whitishness. That's because I downloaded them from the Digital Sky Survey. That's part of the MAST project at the Space Telescope Science Institute. So the Mulcahy Astronomical Survey Telescope, or MAST, and with the Space Telescope Science Institute's digitization of the Palomar Digital Sky Survey allowed me to take these interesting images and download them and pull them in. And notice all of these images that are labeled with the MAST Earth Survey, I used the size of approximately 60 arc minutes on a side. So these are 1 degree by 1 degree images. So if you were to actually go outside and hold your thumb out at arm's length, your thumb is about a degree across. So each of these images is literally a thumbnail in the sky. And you can see just how big they are. All right, so the next kind of cluster is called a globular cluster. HR diagrams from the show that they're about 10 to 13 billion years old. So they're incredibly old. They have big red turnoffs, and there are absolutely no blue main sequence stars. None. There are no O, B, A, F, or G type stars in any globular clusters. There are tons of red giants and no supergiant stars. And there's an incredibly prominent horizontal branch. There are bluer, and there are slightly bluer and fainter main sequence stars, and they are slightly fainter main sequence stars. Why? Because they have less metals. Metals means any chemical element heavier than helium, such as carbon, nitrogen, oxygen, and they are that lower metallicity is a distinct difference in population, which we'll see when we talk about the Milky Way itself. So let's do a sample of globular clusters. Globular cluster M55 is in Sagittarius, and it's over almost 18,000 light years away. And again, these images are from the DSS, from the Space Telescope Science Institute, and they use the same proportions, about 60 arc minutes on the side, so you can see how big they are. So each of the open clusters is about the same angular size, But notice that because these things are much more distant, they're much, much, much larger. This particular globular cluster is about almost 300,000 times the mass of the sun, and it has only about 1% of the carbon, nitrogen, oxygen that all compared to all the stars that are close to the sun or in open clusters. So they're distinctly different stars. NGC 2808 is another globular cluster in the constellation Carina, visible from the southern hemisphere. And it's one of the most massive clusters. It's about 1 million stars, and it's about 12.5 billion years old at a distance of 30,000 light years, or about almost 10,000 parsecs. Yes, it looks small on this degree by degree on a side image, but that belies the density of stars that are situated inside of that. And the total mass of this object is about 1.4 million times the mass of the sun. So this thing is a real seriously massive object with lots and lots and lots of stars, and it's ancient. Okay, so M92, Messier 92, is a globular cluster in the constellation Hercules at about distance about 30,000 light years. So it's not as massive or as bright as the previous one, as NGC 2808. But it's a Messier object. But it is one of the more bright objects in terms of its absolute magnitude. It's also one of the oldest, and it has a mass of over 200,000 times the mass of the sun. This is a picture I took myself. I took this using the eye telescope, remote observatories, and this is of the Great Globular Cluster Messier 13. It's in the constellation Hercules, and it's a wonderful thing to go see, and it's definitely a binocular view, and we see two bright stars on either side of M13, and even a little galaxy just off to the right. And there's other fuzzy features in there that are also other galaxies too. But the globular cluster is dead center, and it's got some variable stars in it. And with that thing, that variable star that's embedded inside of the globular cluster can be made out with large telescopes. It's about 22,000 light years away and about 150 light years in diameter, and there's about a few 100,000 stars in it. And the globular clusters are so dense in general that if we were inside of them, if the sun were inside of them, somehow orbiting some distant star, then we would never experience night because the sky would be so bright with so many stars. And here's an interesting globular cluster, M80 in Scorpius, about 30,000 light years away, about 100 light years in diameter. And what's interesting about this one is it's got a lot of blue stragglers, meaning stars the cluster itself is so incredibly dense that stars can actually collide. And when they collide, that makes them more massive. If that makes them more massive, that makes them bluer, that makes them hotter. And this particular study by Dr. Scherer at the Museum of Natural History, using the Hubble Space Telescope, actually shows the color of globular clusters, which tend to be much, 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 much redder. And that's a real critical thing that we look at. And I did actually a very interesting lab activity that details how you can actually make an HR diagram from the data that Dr. Scherer collected from the Hubble Legacy Archive. So send me a note if you want to do that lab on your own. Messier Object 9, well, we're looking really deep into the center of one of these things, is a near globular cluster. And again, now this is not a 1 degree by 1 degree. This is a close-up picture taken, and the credit is from the National Optical Astronomical Observatory, or NOAO, for this particular thing. It's about 5,500 light years from the galactic core, so it's really near to that thing. And its distance is about 26,000 light years away, and very, very bright compared to the sun. And there's lots of variable stars have been found. So it's interesting that variable stars are present in large numbers in globular clusters, but not so much in open clusters. But this is a big one though. This is Omega Centauri, NGC 5139. It's about 16,000 light years away, and it's the largest globular cluster in the entire Milky Way. It's about 150 light years across and has over 10 million stars in it, with a total mass of about 4 million solar masses. Interesting that the mass is less than the total number, and that's because all the big stars are gone. And Omega Centauri is also distinctive in that it may actually be originating from a disrupted dwarf galaxy that encountered the Milky Way. Now, this is, again, back to the DSS Space Telescope Science Institute image. So you're looking at something that's about a degree across. This object in the sky is about half the diameter or 3/4 the diameter of the moon, or about half the diameter of the moon. So if you go to the southern hemisphere when Omega Centauri is up and you're in a dark sky location, you can see this thing and it looks like a fuzzy star in the sky. And that's what you're looking at, Omega Centauri. If we then check out the globular cluster 47 Tucanae and just look at this is a Hubble Space Telescope image and a study. So the big image is on the left and the study is on the right, and we see that most of the stars in Tucanae 47 Tucanae are red or yellow. And therefore, if we look at the HR diagram, and the left is the center downtown area of Omega Centauri taken by Hubble Space Telescope Group, we see if we make an HR diagram of those stars, we see a main sequence turn off, we see red giant branch, we see horizontal giant branch, we see white dwarfs, but most of the stars are red. In fact, all of the stars are red. The reason they look blue in that left-hand diagram is because the image was taken with narrowband filters, and relative blue was taken compared to relative red. So a color magnitude diagram for a globular cluster such as M55 will have a main sequence, a rather thick, low red main sequence, and that main sequence will indicate mostly K and M type stars. And mass decreases down the main sequence. So low mass stars are there. So we have relatively low mass stars to begin with that are less massive than the sun, if it's going to be older than 10 billion years. And those things will be much smaller. So the red giant branch are extraordinarily evolved stars. They've dead and gone. So they're off the main sequence. They are no longer burning hydrogen in their core. Something has changed in them, and they have changed to become red giants. And some of the stars are blue giants, and those blue giants are a result of now they're not just burning hydrogen, but they're probably burning helium, and that's where the atom. And then we have the blue stragglers, which are, because this is a globular cluster and it's an extraordinarily dense environment, stars can collide together to form a new star, and those stars are more massive than their progenitors, and so therefore they are bluer and hotter, and they're called blue stragglers. And then we have a smattering of white dwarfs, which are dead stars. So what we look at with the main sequence is that you can read the cluster diagram. Now remember, in the main sequence, massive stars are hot, they have high temperature and high luminosity. Low mass stars are red and cool with low luminosity. And as we saw previously, on the lifespan of stars, main sequence lifetime depends only on its mass. Massive stars live a very short period of time. Low mass stars have a very long period of time. And the lifetime of the main sequence compared to the sun is roughly goes to the inverse of the mass compared to the sun to the third power, to the cube. So a 10 solar mass star lives 1,000 times shorter than the sun, and a 1.1 solar mass star lives 1,000 times longer than the sun. And therefore, low mass stars even take longer to form than high mass stars. Stars live a life, and that's what's interesting about all this stuff. Stars have a definite lifespan. And so why? Because gravity pulls it in and the heat pushes it out. And then eventually it runs out of fuel to create the pressure. As it ages, there are internal changes. Hydrogen becomes helium, and therefore there is no fuel left. And if that happens, the internal changes deep in the core have external consequences, meaning the star changes its brightness and changes its color. And as it does so, that means its position on the HR diagram changes. As a star runs out of fuel in its core, deep in the star, that changes how it appears to us in the sky, meaning its color and its overall luminosity. As a star cluster ages now then, if we think about individual stars, that's what we cared about before. So therefore, if we have a group of stars, all with the same age, the stars on the high mass of that happen to be formed in that star cluster, they form very, very quickly, and then the lower mass stars are still forming and don't quite get to the main sequence as the high mass stars form. The high mass stars burn through their hydrogen extraordinarily fast and become supergiants. And then the lower mass stars eventually run out of hydrogen in their cores, and they too evolve off the main sequence. So what that means is that as stars live and die in a cluster, the main sequence peels off the top, and then from the top left to the lower right as the cluster ages. So we're going to see three examples real quick here. The first is the Pleiades. And the Pleiades is, of course, that quintessential nearby open cluster. It's about 100 million years old. And that means only the most massive members, the O and B type stars, have even had time to live out their entire main sequence. And so the upper left-hand corner has a very, very, very beginning turn to the main sequence as they age off their main sequence. But the main sequence is totally in full on the lower right. And in fact, there are some that are still not yet make it to the main sequence. And that's what looks like they're on the lower right. It just kind of veers straight to the right rather than making a nice downward turn left. That means that stars that are incredibly red have not yet completely formed as full stars. And even if that means that the least lowest mass stars can take a very long time to reach the main sequence. Now, if we look at an older star cluster like Messier object number 67, it's estimated to be about half the age of the sun, or about 2.6 billion years. And as a result of that, stars that are more massive than the sun, roughly speaking, something about like stars like Sirius is more massive than the sun, that will have evolved off to become a red giant. But stars less massive than the sun have not yet had a chance to go, because the total lifetime of the sun is about 10 billion years. So if something's 2.5 billion years, we're looking at things that are just maybe at stars that are just about 1.5 times the mass of the sun to about twice the mass of the sun are evolving away from the main sequence in Messier 67. Now, where's the sun on this diagram? If it were in M67, well, that sun's absolute visual magnitude is 4.34, and its color is 0.71. So it would be firmly inside of the main sequence of M67. So that's where the sun would be on this main sequence diagram. I'll use my mouse to kind of show where that is. That's roughly about here-ish or so. So we've got this little point here where the sun would be, but the sun is not in M67. It's not in that cluster. It would be another 7 billion years before the turnoff point gets down to it. So let's look at something that has done that. This is 47 Tucanae, another major globular cluster, and we can see the turnoff point is well deeper than the sun's, and it's about 13 billion years old. And there's nothing that's redder than that, and all of the stars are evolved into red giants, and we're left with K and M type dwarf stars, and that means the age of the turnoff point means that if it's 13 billion years old, this globular cluster is truly ancient and was formed when the universe was only a few 100 million years old. So the stars here have seen the beginnings of the universe. So let's look at them in a group, and let's make a model star cluster. So let's pretend that we can follow a star cluster all the way from beginning to end. And once this star cluster forms, let's say we have a long time to watch it. When a star cluster is formed, the stars descend from their from protostellar times until they become main sequence star. And we're introducing a new term called the zero age main sequence, or ZAMS. And that's the moment when nuclear fusion starts in the star. We're going to discuss that in the future in protostars. We talk about that in the future. So the zero-age main sequence is when the star moves, evolves, its exterior appearance gives indication that it's now on the main sequence. And at about 1 million years, we see that the reddest, coolest stars have not yet become main sequence stars. They're still collapsing, so they haven't turned on nuclear fusion in the core. But the bluest, hottest stars have. So at 1 million years, there they go. The most massive stars have evolved already, and that's what's indicated by the little red dot on the upper right. Maybe there's some star that was 100 solar masses, and it formed and is going to die in less than 1 million years. All right, so 10 million years later, the O stars have completely formed. They become red giants, but that's what we're indicating on the upper right. And the B stars are now evolving off to become giant stars. All the most massive stars, they've gone and done their thing. They become red giants. And now the B stars. And now some of the lowest mass stars are still descending to the main sequence, but the G-type and most of the K-type stars have also descended. All right, so now after 100 million years, the A-type stars are now evolving. The O stars are completely gone. The B stars now have become these red giants up to the upper right, and now we're left with the A stars now at the tip of the turn off point. And now the M stars are just starting to get to the main sequence after 100 million years. And finally, after about 1 billion years, all the massive stars are gone. We're talking all of them. Now we're down left to the low mass stars, or F-type stars, and these are just the ones that are turning off. F-type stars are still more massive than the sun, but the B stars are now the A stars are now the red giant progenitors, and the O and B stars are gone. And there's some remnant white dwarfs because some of the stars have become white dwarfs. All right, so now we've got the M stars be finally making it to the main sequence. And after 10 billion years, 10 billion years, we find that the G-type stars are the ones at the base of the main sequence turnoff. There's huge numbers of red giants, subgiants, asymptotic giants, all sorts of giant type stars. White dwarfs are scattering everywhere, and the M stars make up the dominant amount of the main sequence. So we can see that there is a main sequence, a giant branch, horizontal giant branch, and the zero-age main sequence is when the star finally meets the main sequence location. So the main sequence turn-off point is really important because the main sequence turns off towards the giant stars. The main sequence turn off indicates the age of the cluster, and as a cluster ages, the stars turn off at the high masses. So it goes from the high mass turnoff point to the low mass turnoff point. Low mass stars again have redder colors, and the high mass stars have bluer colors. The color of the turnoff point is the indication of the age of the cluster, and vast computer simulations show that this is what happens when stars evolve, or when they run out of fuel and evolve into giants. So old clusters are redder and fainter turnoff points. So the conclusion that we can get from this is that cluster HR diagrams give us a snapshot of how stars evolve with time. And stars, which means that they change. One star will change from being a main sequence star to a giant. And the observations with clusters with ages from a few million to over 15 billion. Oh my goodness. That's my stupid typo. Not 15 billion, 13 billion, 13.2 billion years indicates that there's a lot of our picture from stellar evolution. So when we piece together the story, we see that it's incredibly important, the idea that there's actual stellar evolution, that what happens in the stars in the sky, what we get is that stars actually have ages, and there are consequences, observational consequences to the idea that as stars run out of fuel, in hydrogen in their cores, the external thing changes. So you can make a computer model that says what it should look like, and amazingly enough, that's what we see. So when we compare, say, the H and Chi Persei, the double cluster in Perseus, there's its turn-off point, and we see M80, which is about 12 billion years old, not 15. Goodness gracious, there's nothing that's 15 billion years old. That would be too weird, because the universe is only 13.2 billion years old. So, and we see a distinct group under there. In sum, there's a whole bunch of things that can be learned by looking at clusters of stars, and most importantly, we learn a significant amount of information about the ages of stars and how they do. So very soon, now we're going to be talking about how stars are born, how they live, and how they die. So we've talked much about this nature of what happens when they run out, but let's get into the real details on that. So we're going to go straight into, actually backtrack a bit, and look at how stars form, because we did indicate that, we've seen that, so we're going to take a diversion next time and look at the nature of stellar formation and the interstellar medium. Take a look at these review questions, have a great time, see if you can answer a few on your own, and we'll see you soon.